Okay, this is AP Review Topic 4, questions based on data, and I'm going to go over the problems from your worksheet packet that were not covered in the notes in class. Before I get started, number 1 from 2018, if you choose to go back and redo that problem, I know I did it in your notes, but after a little time goes by, you might want to go back and redo that. Know that the global average on that problem was a 4.5. That'll tell you where you stand in relation to the average student from around the world. Okay, let's begin with the problem from 2017. This was a calculator problem. Grab my calculator. Okay. All right. It says a tank has a height of 10 feet. So some tank has a height of 10 feet. The area of the horizontal cross-section of the tank at height h feet is given by the function a, where a of h is measured in square feet. So far they have not told us the shape of this tank. Maybe it's a cylinder, maybe it's a prism, maybe it's an odd shape. We don't know. All we know is that it has horizontal cross sections, and each of those horizontal cross sections has an area of A of h in square feet. Okay? The function A is continuous and decreases as h increases. Again, that's an interesting piece of information. We will keep that in mind in the problem. Selected values of h are given in the table. So again, so far we don't know the shape of this tank. All we know is that as h increases, the area decreases. So it's definitely not a cylinder, because a cylinder has the same area, cross-section area, as h increases, right? So the bottom of this, I don't know what it is. It might be weird. It might be, it might be some kind of a prism or whatever, but it has some base. And then as h increases, the area of the cross sections decreases. So something like that maybe, where the height is 10. And each cross section has area of A of h. Okay? All right, let's take a look at the problem. Part A, use a left Riemann sum with 3 subintervals indicated by the data. That makes sense because 1, 2, 3 subintervals to approximate the volume of the tank. We're approximating the volume of the tank, and then we have to indicate units of measure. I'm going to bubble that to remind myself not to forget that. Okay, so we're approximating the volume. Never ever just dive right in and do the Riemann sum that they mention in the problem, because you might not be approximating the correct integral. So let's make sure that a straightforward left Riemann sum would approximate the volume. So volume is always the integral of the area, right? Volume is always the integral of the area. And if it's respect to x or h or y or whatever, it's with respect to something. In this case, it'll be with respect to h. And they want the entire tank, so h goes from 0 to 10. So for us, the area is A of h. So this integral gives the volume, period. That integral gives the volume. And now a left Riemann sum would indeed approximate that integral. So this actually is a straightforward left Riemann sum. But be careful before you dive in and do that. So the integral is approximately the value of the left Riemann sum. So let's now go find the left Riemann sum. The base of this first rectangle will be of distance 2. It's of length 2. So 2 minus 0 is 2. For the height of that first rectangle, we're going to use the leftmost y value, so 50.3. And that's the area of that first rectangle. Now we go to the second rectangle. The second rectangle has base length of 5 minus 2, which is 3. So we're adding 3, that's the base length. And then for the height of that rectangle, we use the left y value, 14.4. And that's the area of the second rectangle. Now for the last rectangle, the base length will be 10 minus 5, or 5. And the height we will use is the 6.5, the left-hand side height. Remember, in a left Riemann sum, you will not use the rightmost y value. For a left Riemann sum, you will not use your rightmost y value. For a right Riemann sum, we would not use our leftmost y value. So we've approximated the volume using a left Riemann sum. Even though we have a calculator, we do not have to actually add up these products. Let's do, however, write our units of measure. Remember that we are approximating volume. Our units are feet. So volume will be feet cubed, or cubic feet. I'm going to write that as feet cubed, but you could also write out the words cubic feet. Okay, next up. Does the approximation in part A overestimate or underestimate the volume of the tank? Explain your reasoning. Well, this is where we're going to use this piece of information. Okay, A is decreasing as h increasing, so A is a decreasing function. And we used a left Riemann sum to approximate a decreasing function. So visually, we have a decreasing function, and we used a left Riemann sum. So our first rectangle, the area of that first rectangle would be more than the area under the curve. The area of the second rectangle will be over the area of the curve, and etc. Okay, so our left Riemann sum overestimated this decreasing function, the area under the decreasing function. So that's what I'm going to say. I'm going to say, since we used a left Riemann sum to approximate the area under a decreasing function, our approximation is an overestimate of the actual volume. Okay, make sure that your sentence, your statement makes sense. Okay, you guys are all great English people. You guys can all write a good sentence. Make sure it makes sense. So here's what they will be looking for specifically. They are looking for 3 key phrases: left Riemann sum, decreasing function, and then your answer, an overestimate. Those are the 3 key things that they're going to be looking at in here. Okay? All right. And by the way, one note to make. I drew this picture just to help myself and you guys. Okay? AP does not need to see that picture. Okay? Not only do they don't need to see it, it's okay to have it on your paper, but your sentence needs to stand alone. Do not in your sentence refer to your picture. I have kids all the time saying, it's an overestimate because of my picture or something like that. Don't say that, all right? Use the picture to help yourself, but your statement needs to stand alone without reference to any kind of drawing. Part C. the area in square feet of the horizontal cross section at height h is modeled by the function f, given by this. Okay, well that's interesting because that's exactly this area in square feet of the horizontal cross section is exactly how they described A up here in the table, right? So now in part C they're saying, okay, now we're going to let F be the area, the cross section area, and based on that model find the volume of the tank. We did the same thing in part A. We estimated the volume using this A, and now this area, and now they want us to approximate the volume using that area. My equation for volume is going to be very similar. It's going to start off like that, except now in place of area, I'm going to use f of h. So the volume will be the integral from 0 to 10, because the height of the tank is still 10, of f of h dh. Integral of the area gives you volume. Okay? But in this case, we have a calculator, and we're going to just stick that in our calculator. Okay? Am I going to need that in part D? If so, I'm going to put it in for y1 using the model from part C. I am, so I'm going to put that in for y1. I have this stuff in here. I'll just leave that there. Okay, so 50.3 divided by parentheses e to the 0.2h plus h. I double check, make sure it's right. Okay, and now I have math 9, 0 to 10. F of h is my y1. And this will give it to me, 101.325. 101.325, and that's the only answer they would accept there. All right. Now it says water is pumped into the tank. Water is pumped into the tank. When the height of the water is 5 feet, when the height of the water is 5 feet, so they're saying when h equals 5, the height is increasing at the rate of 0.26 feet per minute. So they're saying the height is increasing at a rate, that's dh dt, is equal to 0.26 at h equals 5. I'm going to write that down. dh dt, when the height is 5, is equal to 0.26. It's increasing, so that rate is going to be positive. Okay. Using the model from part C, find the rate at which the volume of water is changing. We want the rate at which the volume is changing. So we want dV dt when the height is 5. So we want dV dt when h equals 5. All right. So I need to come up to my part C and get my equation that I have for volume, and it will involve h, and then I will need to take the derivative of both sides with respect to t, right? All right, so I pull out my equation for volume from above. Here's my equation for volume, okay? And I want to, you know what, I said 10 up here. It's not going to be 10, is it? It's going to be whatever the height is at that time, okay? So at that, it's going, I want dh dt here, not, I don't want it to go all the way to 10, right? I want my equation for volume to be flexible depending on what the height is. So, first of all, again, this might be a little confusing having h's here and an h there, If you prefer, you could make these h's like x's or t's or some other variable. That's fine. I don't mind you leaving them h's as long as you handle this correctly. But if it helps you, you could change that to maybe x's, something like that. Again, it's not necessary, but if it helps you keep those straight, you can. So I want to take the derivative of both sides with respect to t. I want to do that. The problem is this is going to have h's in it, isn't it? So when I take the derivative of both sides with respect to t, should have left myself some more space over there. When I do that, I will get dv dt here. That's what I want. So that worked out good. My problem is over here. I have to handle this right. I'm taking the derivative of an h function. It will have h's because of this. I'm taking the derivative of a function of h with respect to t. So we have to do implicit differentiation here, or in other words, the chain rule. Okay? So we are taking the derivative of this h function. We are taking the derivative of the h function. So we're taking the derivative of v with respect to h, but then we have to multiply by dh dt, because that's the implicit part. So it will be the derivative of that function with respect to h, but then we have to multiply by dh dt for the implicit part, for the chain rule part. Okay? If what I just explained is confusing to you, let me rephrase it this way. Look at what I have left over here. Mathematically, algebraically speaking, do you see how these dh's would cross out and you'd be left with dv dt? You see how that's equal? This is a legal thing to do in calculus. You'll do it more when you hit differential equations, but this is a very legal thing to do. Okay? If you want dv dt, then you need to multiply dv dh by dh dt. It's almost like, kind of like a unit analysis kind of thing. I want to be left with dv over dt. Okay? So, first of all, so right here, I want to find dv with respect to h. So I'm taking the derivative of both sides here with respect to h. And that's what we have always done with our second part of the fundamental theorem of calculus. The derivative of an integral, they're going to cancel out. We replace this h with whatever that is. So this will just be f of h. That'll just be f of h. So down here, I have dv dt is equal to, this is just f of h. Okay. Time to plug in my values at h equals 5. Got to tell AP what I'm doing. At h equals 5, dv dt will equal f of 5 times dh dt, 0.26. So, and that is equal to f of 5 I can find by just putting 5 in for h, and then I'm going to multiply that by 0.26. Right? So I have y1 stored in, my f stored in for y1, so y1 at 5 times 0.26. And that gives me my answer. Okay, tricky little problem for sure. By the way, we had to indicate, oops, we had to indicate units of measure. Okay, this, we found the change in volume, So units of volume are feet cubed, units of time are in minutes. So units would be feet cubed per minute. Let's take a look at how this was scored. Okay, in Part A, before they even got to Part A, before they graded Part A, they gave 1 point for units in parts A, C, and D, So you had to get the units in, you had to get the feet cubed in A, you had to get the, oh, look what I forgot. So I would not have gotten that point because I failed to put the units of measure there. So shame on me. This is volume, so it would be feet cubed. And I would not have got, I would have had to get the units in all 3 parts to get that point. So I would not have gotten that point. And then the feet cubed per minute would be. All right. Then on to Part A. In Part A, they gave 1 point for the left Riemann sum. And they gave 1 point for the approximation, which in our case was our left Riemann sum. Okay. Part B, this was just worth 1 point, an overestimate with the reason. So just 1 point for that. Part C was worth 2 points, 1 point for the integral and 1 point for the answer. And Part D was worth 3 points, 2 points for dv dt, 2 points for dv dt, and 1 point for the answer. I am looking at that and wondering what they meant by this dv dt, because that would be the answer. So I'm not sure how they split that 2 points up, or if they split it up. I'm not sure exactly what they mean by that dv dt in this problem. Okay. All right. Okay, moving on to the BC problem from 2015. This was number 3, so we don't get to use a calculator with this one, so chances are we won't need it, or who knows, maybe we would like to use one, whatever, we'll see. All right, so it says Joanna jogs along a straight path. For time between 0 and 40 minutes, Joanna's velocity is given by a differentiable function. So the velocity they're telling us is differentiable. Function v. Selected values of v, where t is measured in minutes and v is measured in meters per minute, are given in the table above. Okay, so this is a problem because it deals with velocity and time that I could have put this in our review for the gosh, I think it's our topic 7. It's a review of our vertical and horizontal motion, because she's jogging on the straight path. It could have been placed in there, but anyway, it also has data, so I ended up putting it in here. All right. Part A, use the data in the table to estimate V prime at 16. So V prime at 16 is approximately delta V over delta T, right? Change in V over change in T. That's what approximately the derivative is. We want to choose the values that are closest to 16, so I would use 12, and 20. So this is approximately equal to delta V over delta T from T equals 12 to 20. And no, you do not have to tell AP that, but I'm doing that for you to get you to just always remember the derivative is approximately equal to the average change. All right, so this will be V at 20 minus V at 12 over 20 minus 12. We could reverse those, make it V of 12 minus V of 20 over 12 minus 20, and we would get the same answer. You do need to show AP that. You have to show AP that if you want credit for this problem. So V of 20 is 240. V at 12 is 200. And 20 minus 12 is 8, or you can just keep it 20 minus 12, and that will work as well. Okay? They didn't ask for units, so that's just the estimate of V prime. Okay? Part B. Using correct units, explain the meaning of the definite integral, the integral of the absolute value of velocity from 0 to 40. So this first part of it, this goes back to our study of horizontal and vertical motion, as well as particle motion. The integral of the magnitude of velocity, the integral of the magnitude is the total distance traveled. That's our equation for total distance traveled. If we had particle motion, the V would be a vector, so we would have that square root in there. You may remember that. Hopefully you remember that. But in this problem, since it's just horizontal motion, it would just, this is just the absolute value of V, just like what it looks like. So I will begin with that. The integral from 0 to 40 of the absolute value of V of t dt is the total distance Johanna jogs. We need to use units. Remember, 2 sets of units in every one of these interpretation problems. We've said what it is, total distance. Now I need to get to my units. So it's the total distance Joanna jogs in meters from time t equals 0 minutes to t equals 40 minutes. So it's the total distance that she jogged in meters in her 40-minute run. Okay. And now they want us to approximate the value of this integral using a right Riemann sum with 4 subintervals indicated by the table. So here comes our right Riemann sum. We will have to be careful because we're not just finding the integral of the velocity, we're finding the integral of the magnitude of the velocity. So therefore, up here for velocity, if we have any negative values in this integral, we will make them all positive values. So this negative 220 in my right Riemann sum for the magnitude of velocity, I will write that as a positive. Okay, so this is approximately equal to, okay, we're using a right Riemann sum. So I'm going to begin on the right. We could go ahead and begin on the left. If we began here, you guys, the first base length would be 12, and we would use as the height of that rectangle the 200 because that's on the right hand side of this rectangle. Okay? So it'll be this length times that height. When we go to the next rectangle, it would be that length times this height, etc. Or we can start on the right and say, okay, let's just start with this one. This length times the right-hand side. And then this length times the right-hand side. Either way you do it is fine. I usually start on the right, but either way you do it is fine. So this will be 40 minus 24, and I'm just going to write that 40 minus 24. If you want to call that 16, that's fine. And then we're going to multiply by the right-hand height, so that's 150. And that's our first rectangle. We have 3 more to go. The next length will be 24 minus 20, or 4. You can just write 4 there, times, and here's where we're going to take the magnitude of that velocity, so that height, so that will be 220. If the absolute values were not here, we would write that as a negative 220. The next base length will be 8, or 20 minus 12. And that height will be 240. And for our last base length, it'll be 12, or 12 minus 0, times that height of that rectangle would be 200. So we had a right Riemann sum, and we never used the leftmost height. Okay, I'm looking, I got burned in that last problem, I'm looking to see if I need to use units or anything. If I did need to use units, we're approximating the total distance, so this would be in meters, but they didn't ask me for units, so I'm not going to volunteer them. Okay, part C. Bob is riding his bicycle along the same path. For time between 0 and 10, Bob's velocity is measured by this. So this is Bob's velocity. Okay, T is measured in minutes still, and B is measured in meters per minute, just like Joanna's velocity was. Find Bob's acceleration at time 5. So we're looking for the acceleration at time 5. Acceleration is the derivative of velocity. So I'm going to begin by writing that. So acceleration is the derivative of velocity. So A of t will be the derivative of b here, which is 3t squared minus 12t plus 0. The derivative of 300 is 0. And now we just have to plug in 5. And that would be a safe spot. Okay. We did not have a this was a no calculator problem. So if I did have a calculator, I probably just would have stuck this in my calculator and did the derivative of this at time 5. And I could have done it all at once there. Okay, part D. Based on the model B from part C, find Bob's average velocity from 0 to 10. So we want the average value of B from 0 to 10. So they're asking us for a formula. The average of B from 0 to 10 is 1 over 10 minus 0, integral 0 to 10 of B. Got to know that formula. So this is 1/10 integral 0 to 10 of t cubed minus 6t squared plus 300 dt. So 1/10. Okay, time for this antiderivative. Just 3 little power rules, right? We'll have 1/4 t to the 4th minus, we'll be dividing by 3 here, so 2t cubed plus 300t. We're going to evaluate that from 0 to 10. So we'll have 1/4 times 10 to the 4th minus 2 times 10 cubed plus 300 times 10 minus what we get when we put 0 in for t, and since every term is just multiplied by t, that's going to be a 0. And that's our safe stop spot. I'm looking to see if they asked me for units. They didn't, so we're good. Let's look at how they scored this problem. In part A, that was worth 1 point just for that approximation. Okay, this was just worth 1 point, but remember, you had to show where you got that from, so you have to show this step. This was vital. You could not have gotten that point without that step, and that step. These other two steps are very nice, but you don't have to write them, okay? Part B was worth 3 points total. 1 point for the explanation. That was our interpretation. 1 point for the right Riemann sum. And 1 point for the approximation. So 3 points total. So our right Riemann sum was also the approximation. So by writing this, we got both of those points. Part C, it was worth 2 points. 1 point for uses b prime of t, and 1 point for the answer. All I can say is show all of your work. Show where you get things from. Don't just stick 3t squared minus 12t. You have to say what is that? Where did that come from? How do you know that's A? Well, you know it's A because of what I wrote up here. So this step was important for this problem. You're communicating that you know the process, not just the answer. And again, I said this to you before, when you're completing an FRQ, complete it so that if somebody who knew just a little calculus but not as much as you, complete the FRQ as if they would be able to follow your work. Okay? All right, and then in part D, it was worth a total of 3 points. 1 point for the integral, 1 point for the antiderivative, and 1 point for your answer. So 1 point for your integral, that would be this whole thing, 1 point for the antiderivative, and then 1 point for the answer. Now we're going to take a look at the problem from 2013. This is from the BC exam. It was number 3, no calculator. It says hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup at time t from 0 to 6 is given by a differentiable function c, where t is measured in minutes, and selected values of c measured in ounces are given in the table above. So this is just the ounces in the cup of coffee. T is in minutes. All right. It tells us that c is differentiable. Again, that's something that we will likely need to use in the problem, otherwise they wouldn't be telling us it. All right. Part A, use the data in the table to approximate c prime at 3.5. Show the computations that lead to your answer and indicate units of measure. This is something that I tend to forget. Unless I bubble it, then I'll usually remember it. Okay. So c prime at 3.5. We're approximating it using data. It's approximately equal to the change in c over the change in t from t equals, and now we're going to get the 2 times that are closest to 3.5, that surround 3.5. And the 2 times that surround 3.5 are 3 and 4. So from t equals 3 to 4. Okay, and that is equal to c of 4 minus c of 3 divided by 4 minus 3. Again, you can reverse the 3 and 4 on top and bottom, and that would be equivalent. C of 4 is 12.8 from our table. C of 3 is 11.2 from our table. 4 minus 3 is 1, or you can just keep it 4 minus 3 and call it good. Units of measure. All right, C is in ounces, T is in minutes, so this will be ounces per minute. Or you can write ounces over minute. Okay? All right. Again, you guys, this is what you must write, and your units. That's what you must write. This other stuff just clarifies what for you, and it clarifies what you're finding. It's nice. It's just not required by AP. Part B. Is there a time between 2 and 4 at which C prime is 2? Sounds like mean value theorem. Is there a time? Does a time exist where C prime is 2? And they give us a specific 2 to 4, whereas in the table it goes from 0 to 6. 2 to 4 is very specific, so I'm hoping that when I do delta C over delta T, that is equal to 2. And if I do a quick check, delta C from 2 to 4 is 4, and delta T is 2, 4 over 2 is 2, so this is going to work out just fine. Before I do that step, I like to go ahead and state the conditions that the MVT requires. So I'm going to begin by saying I need to say that C is continuous on the closed interval and C is differentiable on the open interval. So what about this problem tells me that I can make that statement? And it's right here. It's this piece that I underlined. They tell us that C is differentiable, not just on this interval, but for the entire interval. Okay? So C is differentiable, therefore C must be continuous, because for it to be differentiable, it has to be continuous. So I will say C is given to be differentiable. So C must also be continuous. By saying that, I'm saying it's continuous and differentiable everywhere, not just on the small interval that I need it. But if it's continuous and differentiable everywhere, then definitely it's continuous where I need it. All right, my next step is the equation part. So I want for delta C over delta T, I want that to be 2 from time 2 to 4. I want that to be 2, right? So C at 4 minus C at 2 divided by 4 minus 2 is equal to, okay, go to your table. C of 4 is 12.8. C of 2 is 8.8. 4 minus 2 is 2. 12.8 minus 8.8 is 4. So the average rate of change is equal to 2. Therefore, by MVT, there must be a time when the instant rate of change is equal to the average rate of change. That's what MVT says. So by MVT, you don't have to say by MVT. You could just say so. I'm going to say by MVT because I'm so used to doing it, but sometimes I do just to show you guys that you can do it. I would just say so. But by MVT, there must exist. I'm going to use my symbol for there exists. But you could write out the words there must exist. A T in 2 to 4 such that, I'll use my symbol for such that C prime of t is equal to 2. And that's it. Remember that you can come in here and repeat what they give you exactly, just with so there must be. And then just say that. All right, part C, use a midpoint sum with 3 subintervals of equal length indicated by the data in the table to approximate this integral. Using correct units, explain the meaning of this in the context of the problem. So there are 2 parts of this, the midpoint Riemann sum to approximate this and the meaning of that. So first of all, let's use the midpoint Riemann sum to approximate this expression. Okay, so we are approximating the 1/6 outside, you guys, it has to come over here. Do not forget that. Okay? The midpoint sum is only going to approximate the integral. It only approximates the area under the curve, which is the integral. So now here comes our midpoint Riemann sum. So midpoint Riemann sum, let's recall how we do that. I'm going to come up to the table. We need 3 subintervals. Okay, for a midpoint Riemann sum, here's our base of the rectangle. We have one side of the base is 0. We skip 1 and then we go to the next, and that would be our first rectangle. For the first rectangle, the base length is 2 minus 0. The height that we use is the middle height. So this will be the height we use for the rectangle. So 2 minus 0 times 5.3. Then we go to the next rectangle. The next rectangle starts where the old one left off. So it starts at 2, skips 1, goes to the next one. That will be the base length of the second rectangle, 4 minus 2. The height that we use will be 11.2. For the last rectangle, start where you left off, skip 1, go to the 6. The base length will again be 2 because 6 minus 4 is 2. The height that we use is the 13.8. I had a student a year or 2 ago who did this. She went from 0, this is what she had on her paper, like that. So this is the base, that's the height. This is the base, that's the height. That's the base, that's the height. If that helps you, perfect. Whatever it takes, right? So the first base length is 2, which I got from 0 minus 2. You could just write 2 there, that's fine. And the first height is 5.3. For the second rectangle, we are at 4 minus 2, which is still 2, and you could just write 2 there, and that's fine. That height is 11.2. And the last one is 6 minus 4, which is also 2, and you could just write 2 there, and that height is 13.8. And that is the midpoint approximation for that integral. Okay, so that was our approximation. We did not need to use units for that piece. But then it says, using correct units, explain the meaning of this integral in the context of the problem. So what does that integral represent? We need to know that this is the average value of C, because this is 1 over 6 minus 0 times the integral from 0 to 6 of C. So that's our average value function. So that expression is the average value. It's the average value of C, and C is the amount of coffee. So it's the average amount of coffee in ounces in the cup in the time interval from 0 to 6 minutes. In the time interval from 0 to 6 minutes. And reread it. Make sure that it sounds like it's an actual sentence, all right? Make sure that you have two sets of units, ounces and minutes, and make sure that you included average amount of C or average amount of coffee or average C, something like that. It needs to have the word average in it. Okay. Lastly here, part D, the amount of coffee in the cup in ounces is modeled by B of T. So not only is the amount of coffee C up there, but it's also B of T. Using this model, find the rate at which the amount of coffee is changing at time 5. They're wanting us to find B prime at 5. And we can definitely take a little derivative. So B of T, I'm just going to rewrite that. B of T is this equation. So B prime of T is equal to, all right, just take a derivative. So the derivative of 16 is 0. So I'm coming over here and I'm taking the derivative of this. Remember, the derivative of e to the u is u prime e to the u. So I'll have negative 16 times the derivative of the exponent is negative 0.4 times e to the u, like that. That's B prime, and now they just want us to put in 5 for T. So you could write this as 6.4, or you can leave it 16 times 0.4. Either one, it's the same. Or you could write it as a negative 16 times negative 0.4. That's fine too. And then we're just going to put in 5 for T, and that would be our safe stop spot. Let's take a look at how this was scored. In part A, where we approximated C prime, that was worth 2 points. 1 point for the approximation, 1 point for units. Part B, okay, this was our MVT problem. It was worth 2 points. 1 point for C of 4 minus C of 2 over 4 minus 2 is equal to, actually they didn't say is equal to 2, they just left it like that. So if we have that on our paper, that was worth a point. And then the last point was for our conclusion using MVT. And again, you don't have to use the words MVT, but you do need to use the MVT. Even if you don't name it, you have to state the conditions, you have to state this rigorous step, and then you have to state your conclusion. Part C was worth 3 points. 1 point for the midpoint sum, 1 point for your approximation, and 1 point for the interpretation. Okay, the midpoint sum is here, that was worth a point. The approximation was here, that was worth another point. And then for the interpretation, remember they're looking for the average C, or the average amount of coffee. They're looking for the average there. They're looking for ounces and minutes, okay? 0 to 6 minutes. Okay? And then part D, it was worth 2 points. 1 point for B prime of T, 1 point for B prime of 5. Okay, I think, we have. So let's go ahead and do the problem from 2012. Let's read through it. This is with a calculator, so I have my calculator handy. And they give us the temperature of water in a tub is modeled by a strictly increasing twice differentiable function W. Wow. Strictly increasing twice differentiable function W. So we will likely need that. That's very specific. Where W of t is measured in degrees Fahrenheit, t is measured in minutes. At time 0, the temperature of the water is 55 degrees. Okay. I'm not exactly sure why they gave us that, because it's sitting right here in the table. At time 0, the temperature is 55 degrees. So I don't know why they specified that. I'm assuming they're pointing it out for some reason, but we could definitely have gotten that from the table. So anyway, there you go. There's an initial value, but again, it's right there. The water is heated for... Sorry, I had to take a phone call real quick. Okay, the water is heated for 30 minutes beginning at time 0. Values of W at selected time t for the first 20 minutes are given in the table. So the water is heated for 30 minutes, but we only have the table through 20 minutes. Okay. Part A. Use the data in the table to estimate W prime of 12. All right, well, by the 7th problem that we've done here, this should be like very much a given. We know what to do here. So W prime at 12 is approximately equal to delta W over delta T at the 2 times surrounding 12, which for us will be 9 and 15. Okay, so that is W at 15 minus W at 9 over 15 minus 9, which is W of 15 is 67.9, W of 9 is 61.8, 15 minus 9. I'm looking at, do I need to give units? I don't need to give units for that answer, but I do need to use units when I'm interpreting the meaning of my answer. Okay, so that is the approximation for W prime of t. And again, these are the two things that you must show. This is a nice thing to show, but this is what you must show. Okay, now using correct units, we're going to interpret the meaning of this. What does this mean? W is in degrees, T is in minutes, and we're finding W prime, so we're getting the rate of change of W with respect to T at time 12, right? So we're getting the rate that the temperature is changing in degrees Fahrenheit per minute exactly at the time 12 minutes. Okay, so W prime of 12 is the rate, the temperature of the water is changing in degrees Fahrenheit per minute at exactly 12 minutes. Okay? Since this will be a positive number, the temperature is increasing at that value, degrees Fahrenheit per minute, at 12 minutes. You could have said it that way too. All right. Part B. Use the data in the table to evaluate this integral. Using correct units, interpret the meaning of that integral. Okay. So first of all, it says to evaluate, not approximate, evaluate. So there must be a way to find the value of that integral. Let's take a look at this integral. I see the integral of a derivative. I know I'm looking at the first fundamental theorem of calculus right here. And all that is W at 20 minus W at 0. So this is the change in W from 0 to 20, right? Integral of a derivative, first fundamental theorem. Well, we can look up in our table for W of 20 and W of 0. W of 20 is 71. W at 0 is 55. And so that is the value of that integral. Okay? So this integral is just the change in temperature. It's the change in temperature from 0 to 20 minutes. So I will write that. This integral is the change in the temperature of the water, right? In water temperature. In degrees Fahrenheit, because this is degrees Fahrenheit, so degrees Fahrenheit, from time 0 to 20 minutes. Okay, the things that they'll be looking for is the meaning, the change in temperature, They'll be looking for units of your answer. From time 0 to 20, that's important here. Got to give them 0 to 20 minutes. All right, for part C. From 0 to 20, the average temperature of the water in the tub is given by this. Well, that was nice of them. Use a left Riemann sum with 4 subintervals indicated by the data in the table to approximate that average water temperature. Okay? And then we have to say, is that approximation an over or an underestimate? Okay, so first of all, let's do our approximation. So that is approximately equal to, do not forget your 1 over 20. And now here comes our left Riemann sum. 0 to 20, so the whole thing, okay? So 0 to 20, left Riemann sum, come back to our table. Here's our first rectangle, base length is 4. Then we'll use the left-hand y value for the height. So 55.0, so 4 times 55.0. Okay, that's our first rectangle. Our second rectangle, there's our base length, 5. 9 minus 4. 5 times, and then we're going to use the 57.1 for the height. Next base length, 15 minus 9. 15 minus 9. Times that left-hand side, that left-hand height will be 61.8. And we have one left. 20 minus 15 is 5, and we'll use the 67.9 for that height. And no need to add it up, we'll just leave it like that. So note that even though this was a calculator problem, so far I haven't even touched my calculator. I'm assuming it will need to be done at some point, but so far I have not had to. Okay? All right, now I'm looking up here to make sure I didn't need to give units for that. Okay, does this approximation overestimate or underestimate the average temperature of the water in that 20 minutes? So now we go back up to what we read at the beginning. W is strictly increasing. W is strictly increasing. So we have an increasing function, and we used a left Riemann sum. So a left Riemann sum will use this left-hand side as the first height. And then the next rectangle, we'll be using this left-hand side of that rectangle as the height. Remember our Kit Kat bars? We didn't use that one, so we ate it off, and so forth. So our approximation yielded areas that yielded rectangles that all were below the actual curve. So our area will be less than the actual area under the curve. Okay, so I will say that. I will say since we used a left Riemann sum to approximate the area under an increasing function our approximation is an underestimate. Of the actual average temperature. Okay. All right, one more here. All right, now for time between 0 and 25. So this is beyond the data in that table. So for 20 to 25, the function w that models the water temperature has first derivative given by this. That's the first derivative of w over this time interval. Based on this model, what is the temperature of the water at time 25? Well, I have the rate, and I have a value, so I can get any other value with the first fundamental theorem. So I'm going to set up the first fundamental theorem. W at 25 minus W at 20 is equal to the integral from 20 to 25 of W prime. So W at 25 minutes is equal to W of 20 from the table is 71.0 plus that integral. And now for the first time in this whole problem, I'm going to use my calculator. I'm going to grab my calculator and type that in. So I have 71 plus the integral from 20 to 25 of W prime, 0.4 square root t cosine 0.06 t. I'm being super careful here. Okay, I'm hoping I typed that in right, and I got 73.043, and that's the only answer that they would take here. So 73.043. Did I need units? No, so I'm done. Okay, let's take a look at how they scored this. In part A, it was worth 2 points total. They gave 1 point for the estimate here, and 1 point for the interpretation with units. Okay. In part B, they gave 1 point for the value of that integral and 1 point for the interpretation with units. Okay. In part C, it was worth a total of 3 points. 1 point for the left Riemann sum, one point for the approximation, and 1 point for the answer to the last question, underestimate, with reason. Okay, and then lastly, in part D, is worth 2 points, 1 point for that integral and 1 point for the answer. So 1 point just for that integral. Okay, that's it for FRQs for this topic.